So what we are trying to do is we are trying to express this term over here now, right? When we are deriving, right? So the y bar, right, is c plus y multiplied by 0.5, as you can see down here, right? Right, that's our y bar. So this is the y bar. So coming back to our example, so this is 0.0 c, right, is the y max plus by y multiplied by half. Okay, so if we were to tidy things up, so this will be equal to 0.08 multiplied by 0.035 squared minus by y squared. Okay, so at the end of the day, your y bar will be 38 times 10 to the power minus 6 minus by 0.08 y squared, 0.08 y squared. So this will be our equation 1. Okay. So how do we know that this is correct? Okay. How do we know that this is correct? Right? How do we know the expression we form is correct? So we know if we substitute y is equal to 0.035, comma, right, into equation 1, okay, qz should be equal to 0. Okay, so we try. Okay, so we test it out. So qz, where now is 0.035, 98 times 10 to the power minus 6 minus by 0.08, 0.035 squared, right? So 98 power minus 6 minus 0.08 times by 0.035 squared. This thing is in fact equal to 0. Now there's a difference between a student scoring high marks and a student not scoring as high as a mark is the ability to check whether the equation is right or wrong. Okay, so I hope you all embrace this, right? Don't be discouraged or whatsoever. Then finally, we can form the distribution or the equation of the shear stress in the flange, right? So you have shear at the flange is equal to this will be equal to 90 times 10 to the power 3. Then this will be equal to 98 times 10 to the power minus 6 minus by 0.08 y squared. You had your second moment of area, which is what we have is what, 5.813. And the thickness is equal to 0.16. Okay. And then when we put this out, so 90 power 3 times by 98 power minus 6 divided by 5.813 power minus 6 divided by 0.16, so it's equal to 9.483 times 10 to the power 6 minus by 0.08 times 90 power 3 divided by 5.813 power minus 6 divided by 0.16 is 7.7441 times 10 to the power 9 y squared. Okay, right. So once we have this equation, okay, so this is a second order polynomial equation, and it's valid from 0.015 meter y to 0.035 meters. Okay, so this is the equation of the distribution of the shearing stress at the flange. Okay, so the next one is we want to find, okay, so we are going back, so this is just a flange. We are going to find at the top section, okay, the web, okay, the top section at the web. So I'm going to copy this entire diagram. Right. So now we are going to, I'm going to get rid of this. Okay. Yes, I see what I can get rid. Yeah, I can get rid of this and this. Okay. So I'm going to still draw my centroid. Yeah, so that's still our centroid. So next, what we want to find is we are going to find the web section. Okay, the top. As I say, I usually call this top, right? So we're going to find the top web section, and the limits are 0, y, and it's going to 0.015. Okay. So by looking at our rules, if we look at the top web, right? So Vy over Izz Qz multiplied by T. So we know that if you look at the web now, right? So the web, the thickness is 0.02, right? And then you have what? You have left and right, right? You have your left and right web. So the thickness is equal to twice, okay, multiplied by 0.02, and this equal to 0.04 inches or millimeters or meters, sorry, to beg your pardon. So the 2 over here is due to left and right web. Okay, you have to consider the left and right. Okay, so in this case, right, we know that Vy is a constant, Izz is a constant, right, based on rule number 1. Thickness we know already, but we don't know Qz. Okay, now Qz is a bit tricky down here. Okay, so where is our y now? Okay, so I'm going to draw our y. Okay, so this is the point of the y, right? So now this is our y, and if you look at our rules, okay, we look at our rules. I'm going to copy the rules. Where are our rules? They gone missing. Okay, I'm going to copy them again. Right, and one of the rules says the analysis starts from y max. Okay, so this is the y max, right? That over here, this is our y max, right? It starts from y max and come down. Okay, so for this case, we have to consider, right, the area of the flange, and you realize that the area of the flange is going to be a what? Constant. Yes or no? And then you have to consider the 2 areas, sorry, of the flange is constant, then the variable of the web is a variable. Okay, let me repeat. The Q, first moment of area for the flange, is a constant, right? Because of the limits, right? It go from 0 to 0.015. But we have to consider the flange because the analysis starts from what? Y max. Okay. Then after that, we consider the area of the web, which is a variable. Okay. So now we are going to look at let me put the rules on the side. So we are going to look at QZ, or summation of QZ. So this is equal to QZ of the flange plus by QZ of the web. Okay. So this will be equal to the width, which is 0.16. Right. The depth is equal to 0.02. Right. And then the y bar is equal to 0.035 minus by 0.02 divided by 2. Okay. Okay, so when that's the case, so 0.02 divided by 2, 0.035, 0.0. Okay, then you plus, right? So the web twice for left and right, right? The width is 0.02, right? The thickness, the depth now is equal to 0.15. Sorry, 0.015 minus y, right? And then 0.015 plus by y, and then the whole thing multiplied by half. Okay. So this will be equal to, so 0.035 minus by 0.01 times by 0.02 times by 0.16 is equal to 80 times 10 to the power minus 6 plus by 0.02, okay, plus by 0.02 multiplied by 0.015 squared minus by y squared. Okay, so if you were to remove the bracket, so this will be equal to 0.015 squared times by 0.02 plus by 80 power minus 6 is equal to 84.5 times 10 to the power minus 6. And then you have minus 0.02 y squared. Okay. Right. So from here, we are going to plug into how to find our shear stress distribution. Okay. Shear stress distribution of the top web, right? So you have shear, right? So V is equal to I forget what's up, 90 times 10 to the power 3. Your Q is 84.5 times 10 to the power minus 6 minus by 0.02 y squared, right? Divide by I, which is equal to I have very poor short-term memory now. 5.813 10 to the power minus 6, and then the thickness, we knew our thickness, right? Our thickness is equal to 0.04, right? So this will be equal to 90 power 3 times by 84.5 power minus 6 divided by 5.813 power minus 6 divided by 0.04 is equal to 32.707. Right, times 10 to the power 6 minus by 2 divided by 5.813 minus 8. Minus by 7.74